Ladies and gentlemen, I welcome you to another exciting presentation about artificial neural networks. Today I'm going to speak about distributed artificial neural networks, ANNs, and intend to clarify the need for harmonizing them. We will have a particular look on the effect of different activation cycles and activation rates. The multi-site setting of Industry 4.0 plans serve as application context. However, you can transfer results to any forms of AI-based application systems. Let's start right away with the first agenda point. Let's find the motivation for researching interwoven cognitive production networks. Typically, in a first step, Industry 4.0 machines are associated with digital twins. Using the concept of neural modeling, CONM, machines are mapped to neuronal twins. So far, these neuronal twins already have been brought into interaction to produce goods. You can find the article at Grum 2021, numerous presentations about this at YouTube. In the figure above, you can see the prototype of a first AI-based production system using this kind of concept of neural modeling. Simulation proved neuronal twins to induce productive behavior, which is great. Further state-of-the-art shows new concepts and tools to detect artificial knowledge of AI-based systems. In the figure you can see knowledge objects visualized by algorithms which have been extracted from artificial neural networks, these ANNs. These have made the productive behavior of neural twins plausible. Further, production processes induced by interactive ANNs can be explained and improved by them. Now please imagine to focus on process chains, such as global production processes with multiple sites. So we have production sites at multiple locations. Each site is neuronally substantiated with the concept of neural modeling. Thus, we are speaking about interwoven cognitive production networks. Of course, goods are produced in a certain order. This order goes along with artificial knowledge patterns that are emitted because of a required production sequence. The problem here is we have different vendors, different company standards, different IT systems, etc. All of them lead to different ways to use their neuronal twin, which means they have individual activation points in time and individual activation velocities. So, the research question in the first step is, how can different activation types of rate and cycle combinations in multi-site artificial neural networks be researched? If we are able to research these, we can examine effects of different activation types next, which is the reason for presenting two papers today. The first presents the research instrument, and the second presents the first experiment results. Let's now face the creation of the research instrument first. Principally, the research was realized as a design science-oriented research. Requirements were collected and the simulation system have been set up. Experiments were designed and multi-site ANNs have been demonstrated and evaluated. However, for setting AI-based systems up, the concept of neural modeling has been essential and its proceeding. To simulate a global production chain, 4 production sites were conceptualized. Each has had different ANN-based production machinery and different production tasks. At the first 2 kinds of production sites, fruit is prepared for marmalade jar production. The marmalade jar were produced at the 3rd production site. The 4th production site produced labels and attached them to the marmalade jars so that they can be brought to custom retail. A first collection of ANN-based machines cared about the fruit production and refinement. 3 kinds of fruits, namely apples, bananas and oranges, were provided by the postman, prepared and controlled by machine 1, and transported to the right of the short conveyor. A transport to the next machine location was realized by the long conveyor, which overtook the workpiece carrier from the short conveyor. Machine 2 then refined and controlled the fruit carriers. Finally, nice fruit was released at the right of the long conveyor, here. The Fisher technique-based production site, so the third production system, realized the marmalade cooking process. There is a storing area for fruit purchased. You can find it here. There's a cooking machine production for the jar. You can find it here. There's a packaging station filling the marmalade into glasses and closing them. Closing the jar lid. You can find it here. Or here. And finally, there's a sorting machine for delivering the jars. You can find it here. Next, you can find the modeling items of the NMDL, which are substantiated by artificial neural networks. The Lego-based production site is used to print labels onto the jam jars. Details about its production process can be found at Grum 2021. For an overview, the jars are produced by 2 machines at the left . You can find them here. It's transported to the right with a conveyor. Then it's transported via the robot arm from this conveyor belt to this conveyor belt. It's transported via the conveyor from the left to the right and finalized by the machine you can see here. So coming back to the overview production process and bringing all the layouts together. The real machinery was set up, was constructed and positioned like this. As the effect of inefficiencies were the focal point of simulation, modifications of the ANN activation were installed at the first 2 production sites. I have highlighted them here at the corresponding perspectives on the systems. So, inefficiencies coming up at early production sites can be observed at consecutive production tasks and production sites. Each production site's machine was set up as a MQTT client so that the simulation system managed communication flows among different production sites. The communication management of real-world systems and controlled scenario simulation, which is in the sense of experiment designs, is not trivial, so a communication flow has been designed. Focusing on the first 2 production sites, each site has had to realize continuously AI-based picture analysis tasks and AI-based transport analysis tasks. The simulation control triggered ANN requests based on the simulation clock and the experiment design. So, based on the images and the sensor values taken at the physical instance of the system, the neural twin was required to decide about the required transport activity and derive machine instructions. In the interplay of numerous ANN-based production machinery, these instructions should lead to a productive joint production behavior. Let's face this productive behavior with the help of the neural modeling and description (NMDL) process view. Here you can see the detailed view on the process that was to be induced by the ANNs of the first 2 production sites. Indeed, there are scenarios that ask for machines doing nothing. So much about productivity, and yes, you need pauses for being productive too. Here you can see idling tasks that are required by the ANNs. Here you can see the detailed view on the induced process that asks for machines activity at the first two production sites. Please be aware, this process summarizes the process instances that are not disturbed by inefficiencies and errors. Everything works nicely as it should work, so we have a look on something like the reference scenarios. Let's have a look on its details. The first part of the process cared about the initialization of the simulation setting. For instance, this referred to the workpiece provision by the postman. It further cared about the autonomous localization of each machine within the machine's environment. Here and here. For instance, the conveyor orientation should have an effect on the outcome of the ANN using for instruction the machine. In the one orientation, the workpiece carrier was to be transported from the left to the right, and vice versa in the conveyor opposites orientation. The second part of the process cared about the fruit preparation and control before delivery. So, either the fruit was nice and the workpiece carrier is delivered, that's the upper control flow, or the fruit showed bad quality and the workpiece carrier was reclaimed, that's the second control flow. The third part of the process cared about the fruit transport to the second production site, the refinement and control before delivery. So, either the fruit was nice and the workpiece carrier is delivered, that's the upper control flow, transport and the delivery, or the fruit showed bad quality and the workpiece carrier was reclaimed. That's the lower control flow and the transport back. Apparently, here becomes clear, an AI controlling task is realized twice, so the AI controlling engines can be reused here. Maybe you can recognize this kind of redundancy in the next slides. On the left, we can see the activity view of the NMDL on the AI-based picture classification of machine 1, so the first production site. On the right, we can see the corresponding version of machine 2, so the second production site, and the kind of redundancy I mentioned before. The RGB values are inserted in the ANN. Here you can see the pixel information X and Y axis of the R values, of the G values, and of the B values. The ANN, which is represented by this kind of modeling element, classifies the corresponding type of fruit. So here you can see the types of fruit recognized. For this simulation, more than 5,760 ANNs have been trained and released via Docker's Hub, so that you can reuse it and redo the experiments. The neural networks for AI-based picture classification were designed based on this structure. We have repetitive, convolutional, and pooling layers. Their task was to detect relevant patterns within the pictures. We have attached here a feed-forward structure. Its task was to identify the correct labeling on the basis of picture patterns worked out by the previous ANN structure. The output structures of the picture analysis components were attached to the neuronal structures, the next neuronal structures. So here you can see the outcomes of the previous ANN, which are inserted in the kind of N which is represented by this modeling item. The cyberphysical's individual environment perception served as further activation input. In the case of machine 1, it referred to these modeling entities. In the case of machine 2, this referred to these kind of modeling items. The IA-based transport classification combined these kind of reality perception and derived a decision on these three guys: the transport to the right in the case of no quality defects, the transport to the left in the case of claims, and the idling in the case of no workpiece carrier is available. Further, facing these two modeling guys, the AI decided on the availability of an alarm situation and claim presence. Since the ANN needs to establish an understanding of time in regard with the duration of transports and further production tasks, a long short-term memory structure was created. So you can see the NMDL's 3-cell LSTM block for the first time at this kind of presentation. We have the 3 cells right within the LSTM block. The input neuron you can find here, the forget neuron you can find here, and the output neuron you can find here, the output gate. Right on the left you can find the input neurons, and right on the right you can find the output neurons. So much about the design of the ANN-based simulation environment for multi-site ANN-based systems, and the example of global marmalade jar production chain. Please find further details, the process views, etc. in the articles mentioned. Let's now face the experimentation. Let's face the general experiment task. There should be at least 2 neuronally instructed production facilities. Further, experiments should vary activation types in regard with activation cycle and rates. The effect will become apparent in the context observed, which here refers to the production operations that can be investigated now. Simulations have stressed ANNs being activated at delayed activation cycles and variations in activation rates. Focusing on the smallest set of variations, these variables have led to a 2x2 experiment design. For each of those experiment design matrix elements, a hypothesis has been derived. Hypothesis 1. The synchronization of activation cycles with the same activation rates of distributed production sites promote the trouble-free operation of production chains. Hypothesis 2. Decoupled activation cycles with equal activation rates of distributed production facilities lead to disruptions in production chains. Hypothesis 3. Different activation rates in synchronized cycles of neural systems of distributed production sites lead to disruptions in production chains. Hypothesis 4. Different activation rates in asynchronized cycles, in the opposite sense of a standard of distributed production sites, prevent the operation of neuronally instructed production chains. What has been measured and analyzed? There are multiple options. Some of them are selected here. Let's focus on the first experiment first. The behavioral analysis shows the following for the 3 production periods simulated. So I'm having a look on these two colors here. The black production side and the blue production side show the same activation time points, so the same cycles, and they have the same rates. Here, workpieces are provided in time. Picture analysis and transport analysis are perceiving workpieces as desired. At the second CPS, in total, 2 productions are finalized that can be provided for later production sites successfully. So efficiency analysis counts no inefficient image analysis and idling tasks. Let's focus on the second experiment now. The behavioral analysis shows the presence of problems. These come up because neuronal instructions are overwritten. Further, the transport instruction is interrupted because due to interim activations, the workpiece perception is lost between the sensory perceptions of the systems. In total, we count quite a lot inefficient analysis and idling tasks. These are not productive. They even disturb the trained production order. Thus, at the second cyber-physical system, in total, no productions are finalized successfully. Consecutive production sites will notice supply bottlenecks. In experiments, I have counted numerous inefficiencies due to false activation organization in these interwoven cognitive production networks. In reality, we are mostly faced with the production behavior only. Debugging the underlying neuronal systems is effortful and a long-lasting task, but we experience the influence of activation types on these disturbances and inefficiencies. Aiming for a sustainable AI use, why don't we use these insights? Regrettably, system analysis and chaos theory only focuses on the identification of chaos or different states of equilibrium. There's no further differentiation. What we need is an activation type related state description. The vision, if we can identify the source of chaos and the respective state description of chaotic situation, we can restore efficiency by guiding ANNs. So facing all kinds of variations of two activation types, I mean the coupling of activations as well as the relation of activation rates, I systematically derived further kinds of simulation scenarios. Similar to making music or clapping hands, activation points of time can be in time, coupled, or delayed, or early, decoupled. A further kind of organization can be identified if the activation rates are the same, divisible, or duplicable. For instance, if a later production site is activated twice as often, half of the activations is not productive. However, if it is activated right at the time, production processes will work as desired. Just for orientation, in this presentation, or respective the article, only 2 scenarios have been presented in depth, ID 1 and ID 14. I highlighted them in red. The exciting thing is, if we are now able to classify the activation type, our ANN systems, by one of these 14 new states descriptions, we can intervene by management in order to restore inefficiencies. Just for an impression, on the left you can see the naming of the 14 novel kinds of state descriptions. The detailed characterization you will find in the corresponding paper. From these concrete management interventions have been derived. You can see some examples on the right. So let's face a simple example. Imagine a second production site has the same activation rate as the first production site, but it's delayed. By management intervention, you can shift the retarded activation to the point in time. Then disturbed ANNs are harmonized and production will run smoothly. Further example, if sensor perceptions are overwritten due to speedy activations, you should buffer them. So you guarantee a second production site to have relevant information in time of activation. So let's come back to the initial research question and find the answer. How can different activation types of rate and cycle combinations in multi-site artificial neural networks be researched? We have seen components from 2 articles. The first article has focused on the research instrument creation. A simulation setting has been constructed representing multiple production sites. Here, each site is represented by individual ANNs. Simulation scenarios have been worked out, as well as underlying NMDL processes. Further, an experiment design clarifies how to manipulate activation rates and activation cycles systematically. The second article has focused on the demonstration and experiment realization. Novel forms of rhythmic state descriptions for dynamic systems have been designed. These systemize variations of activation types. The effect of activation types on real-world behavior has been proven. The analysis of machine behavior and neuronal patterns have uncovered inefficiencies and production failures. Further, state-specific management interventions have been derived that are capable to deal with inefficiencies and restore efficiency. Their implementation and experimentation will follow next. Here you can see the references, and thank you for your attention until here.